Thank you. I want to thank the organizers for this opportunity to speak about my research in the last 4 years, although the origins of and the original ideas for these topics were when I was 12 years ago at IHES in Paris. I had an opportunity to learn about fibrations from the master, late Jean Benabou. There were many questions which are still open, but I will try to somehow emphasize the importance of fibrations once more, because we all know that they are all around mathematics, theoretical computer science, and so on. But still, there's a lot to discover about them. People usually say that this is a folklore knowledge, but when I start to investigate about their structure, I realize how many layers of the structure there are. So I apologize in advance for many diagrams with which I will torture you. Some of them I will skip. I will rather speak about some deeper aspects, but I couldn't avoid them. And some of them I put just that you are aware what complexity is needed in order to axiomatically define fibrations in a way which was never done before. So I will start with Lax two monads and Lax algebras in the sense of Marta Bunge. There's a paper from 1974 when I was born called Coherent Extensions and Lax algebras, in which she introduced Lax two monads in order to axiomatize relational algebras, topological spaces as relational algebras over the ultrafilter monad. So the definition is such that you have a colax functor on the two category. There's a typo, it's not from A to A, K, never mind, K equal A. There's a unit colax transformation, there's a multiplication, and there are families of these two cells, which in special cases will become two cells present in a fully faithful adjoint string, but we will come to that. I will just show you the diagrams. What are the defining conditions for the colax two monad, just that you are aware that they are a little bit complicated than the strict two monad, although our case, and that is strict associated split fibration two monad and associated split cofibration two monad, are special cases of these. But these, I will go through these diagrams because they just so that visually you see that they are remind you on triangle equalities, but in one dimension up. So these rows and etas are present also in the ordinary definition of a monad. So I just know that this is a categorification on the dimension n equal 2 of the usual notion of a monad. So there's a notion of a Lax algebra for a Lax monad. It is composed of an object of a structure cell psi, and these two cells, which satisfies three axioms like this. Again, very similar to triangle equalities. This is the first one. This is the second one, in which you see that the great care is needed when you deal with colax functors or Lax functors, because they are coherently associative only up to non-invertible two cell. So it is important just to keep in mind that all the structure need to be preserved, and therefore to insert right two cells at right places, which is somehow very painful when you investigate it. And this is the last axiom for the Lax algebra. I didn't want to bother you with these technical details, so we will move to the core of the talk, and this is the special case of the Lax algebra, and this is a associated split fibration two monad. So for those of you who dealt with fibrations already, you may know that their axiomatization is mostly done first by Grothendieck, of course, but mostly done by Jean Benabou and several other people, but the fact is that they investigated only the case of the fixed base category. What I did, in which one cells are triangles. So if you have two fibrations, they have a common base, and they have a horizontal functor, which is a morphism between them. Those which preserve Cartesian morphisms, we call Cartesian functors. They have special properties, very pleasant. But I moved on in order to generalize this situation in two aspects. One is that I considered variable bases, so I allow all categories to be in the base, not just a fixed one, B, so that you, and also I allowed to squares to be filled with two cells, either pointing upwards or pointing downwards. So this is the example of such a square. The front and the back sides are comma squares. So this is the definition of the associated fibration, because, for example, if you look at the back side, you have a functor P from E to B, and it is to this functor we associate so-called associated fibration. So it is domain. This F of P is. Can you hear me? This is a domain projection. Sorry about that. So this comma category has objects. B is an object in B. There's an object E in here in E, and they are connected with morphism F in the base B. So F goes from P to E, like here. Okay. And this is the definition of the associated split fibration, because it is a split fibration with a canonical splitting. I may say here that, so here what you see is that we are starting from the two category of, I will call them colax squares, where objects are all functors. One cells are, look like right face of the cube, and two cells look like cylinders of these right faces. So how does this two monad acts on one cells and two cells? Well, if you have one cell from between two, first, if we take this right side of the square, how we define the action of two monad on this one cell. So it will be a, again, it must be, in order to be well defined, a square filled with two cells, which is defined for any object, BPQ, like in the last slide, like this. You apply U on B, also you apply it on P, and then post-compose with two cells which look upwards, and F of V. And here you can see that the definition is well defined, because so P, which goes from B to E, first you apply U, and then you post-compose with BE, and the result, this vertical thing, is the object in C C comma Q. So this codomain. So this is the action of the two monad on one cells, and of course we have it on two cells of the type UE, where U goes from E to B prime and E goes from E to E prime. There's a commutativity of this diagram which says that the action is well defined. So with a lot of work, one can, fairly lot of work, one can prove that the two functor which I just described is underlying two functor of the colax idempotent two monad, this time defined for all bases and for all squares which are filled with two cells which look upwards. I didn't have time, and I must be careful about time, to use the slides for the other type of squares, which are squares with two cells which look downwards. But when I investigated how to define an action of a split two fibration of such two cells, I realized many things which are connected not just with fibrations but with other kind of structures like Chu construction. I will tell you more about it when I will just describe how these functors. Maybe these diagrams are not that important to understand. They are present here just that you are aware that definition is well defined also on two cells, because two cells are cylinders. We have B on this side, beta on this side, internal side, and gamma on the outer side. So this is just the definition of a split of the fibration. Two monad on two cylinders, and the diagram on the right, and its commutativity verify that the definition is well defined. Here we have a components of the unit of our two monad. So what happens is that on the right side you have a square in which back and front face are comma squares by definition. This one here is also on the right side is a comma square, which is peculiar because it gives a definition of a multiplication. Comma squares of the same types are on the right side and the front side. On the back side, it's a bit different, but these are responsible for the definition of the multiplication, this one, which is of course part of the definition of a two monad. So this two monad is special because this EP will turn out to be a co-unit of a comonad, which is a close cousin of this strict two monad. I will not talk about it, there's a limited time, but it's a very special type of two monad, such that unit is right adjoint to the co-unit of the comonad in question. Finally, this unit is defined for any object in the total category. I will say total category because for Jean Benabou, functors were generalized fibrations. That was his philosophy and his approach to mathematics, to consider functors as generalized fibrations. Once when he realized that there's a generalized type of the Grothendieck construction which gives the equivalence between all functors with a fixed base, for example B, and lax functors from opposite of B to distributors. So this is the I established this result also for variable bases and all functors, and I learned that what one can do is that in several situations, for example, notable to theoretical computer science, we are not always confronted with fibrations per se. Some desirable properties in theoretical computer science have functors which are ought to be fibrations, but they are not. Either you can restrict the nature of the object which represent them on the shift theoretical side. By this I meant lax functors from B up to distributors. So if it is not lax functor but a little bit more strict pseudo functor, you obtain Condorcet fibrations. If you restrict the codomain to cat, you obtain pseudo functor fibrations, and so on. But it is very strange to me that even today the complete axiomatization via, at least from the perspective of two-dimensional monad theory, not just developed. There is no written account of pre-fibrations as lax algebras for these two monads. Although they are present all over mathematics. Well, this is just the definition of the unit of R2 monad, so simply by the universal property of the comma square. The horizontal composition is identity, obviously, which is expressed by this curved arrow, and this is how you obtain a component of the unit, and component of the multiplication is just the image by our two functor of the co-unit of the comonad about two comonad, also lax idempotent, about which I will not talk today. These are the universal properties of the unit and co-unit because I mentioned that we obtain a colax idempotent two monad. By definition, this means that you have a fully faithfully joined string in which the unit of the first adjunction and the co-unit of the second adjunction are identities, it is enough to require only one that it is identity and this imply that the second one is also identity. There's a pseudo-distributive law between fibrations and co-fibrations, by which I mean between two monads, which gives you associated fibration and co-fibration. I didn't mention you how a lot of the structure for obvious reasons. How much time still do I have? 5 minutes. I will be quick. This F with circle means associated co-fibration. It's just the somehow a dual construction to associated fibration, but with a prescription which was given by Lawvere a long time ago, and although in the case of strict two monads, I suspect there's a deeper reason for all these pseudo-distributive laws between associated two monads and their duals, because there is such, for example, distributive law between associated coproduct and product monad. I think that the deeper reason lies in the duality involution of categories. I still didn't prove that, but it seems to me, after I realized that associated fibration is admissible, you will see what that means in a second. After that, I realized that all the most important constructions in mathematics, like associated products and coproducts and duals of these operations, are admissible in the sense of Bunge and Funk. And from today's perspective, I'm surprised that their only crown example of the admissible two monad was a symmetric monad on toposes. I will just give you a diagram which will show the origin of the pseudo-distributive law, because here, what is object here? Well, exactly this cospan. Here you have B, and here you have P slice B. So this is exactly the object of this category, and how the pseudo-natural distributive law is established is that we attack this cospan by U, and then this is the definition, which I didn't mention, but I just wanted to give you a visual impression of it, how the R2 monad acts on the squares with two cells which look downwards. So basically it is given by, this is by precomposition with those two cells which look downwards, and then we make this pullback here. This is one direction. So this is direction which starts here, goes here, and ends up here. Or we can take immediately, lambda p means pullback. So the distributive law between fibrations and co-fibrations is a pullback. So it's universal property. So this universal property allows you once when you go from one direction, that you go in the other direction. You take the pullback in the base, Then you attack it with U, as you see here. You pull back on the backside, and when you compare it here, you obtain your component of lambda. Notice here that if U is pullback preserved, then this will be an isomorphism. And this was the reason why I realized that quasi-topoi, we will not have time to talk about them, but by definition, they are Cartesian closed categories with finite limits and co-limits and sub-object classifier for strong monos. So it was necessary to, if you wanted to define a two-monad, fibration two-monad for both types of squares, then it was necessary that the bases have pullbacks in the case of associated fibration, or dually, that the bases have push-outs in the case of associated cofibrations. Which kind of categories have both quasi-topoi? That was one. There are minimal conditions which are present in so-called essentially affine categories, which have not all pullbacks and push-outs, but some pullbacks of split monos and push-outs of split epis. And there's other condition in the definition, but these are the two branches in which I see that the theory can be developed, at the side of quasi-topoi or at the side of essentially affine categories. And now the crown definition, hopefully I have still 1 minute. We say that for a colax idempotent two-monad, one cell is admissible if when you attack it with the two-monad, you obtain a left adjoint or a right adjoint. So this is the definition of an admissible two-monad. It has all bicomma objects of admissible two cells, which looks like this. So admissible two cells are stable under bicomma objects, and the most important thing which I proved is that the associated split fibration is admissible. There are many, I'm still surprised every day that I discover how many examples are covered by this fact. From the theory which Paul-André Méliès with his collaborators developed in theoretical computer science, there are examples of flux algebras for these two monads everywhere. In Axel Osmond's work of the R theory, right multi-adjoints are admissible objects for these two monads. So it covers a plethora of examples, and I will stop here. Thank you.